Good morning, friends. We derive the equation of the work done for isothermal process. Isothermal process, that means the process during which the temperature of a system remains constant. By using this concept, we derive the work done in an isothermal process. W is equal to mu RT ln V2 upon V1 for the expansion, and W is equal to mu RT ln V1 upon V2 for the compression of a gas. Right? After that, discussion of the isothermal process. The same equation of the work done we derive for adiabatic process. So the question is that define an adiabatic process and obtain an equation of the work done in an adiabatic process. Again, the question is that define an adiabatic process and obtain the equation of the work done in an adiabatic process. Now first, what is the adiabatic process? Already we discussed about the different type of thermodynamic processes. Adiabatic process, that means the process during which the exchange of the heat between system and environment or the surrounding does not take place. That means the exchange of the heat between the system and environment is zero. Such process is known as adiabatic process. Again, the process during which there is no exchange of heat between a system and its environment. No exchange of the heat takes place between the system and environment. That means the system is isolated. System is isolated. Again, the definition of adiabatic process is the process during which there is no exchange of the heat between system and environment is known as adiabatic process. That is known as adiabatic process. Now, from the first law of thermodynamics, delta Q is equal to delta U plus delta W. For adiabatic process, exchange of the heat is zero. That means the delta Q is equal to zero. It means delta Q is equal to, delta Q is equal to 0 is equal to delta U plus delta W. It means delta U is equal to minus delta W, or delta W is equal to minus delta U. Again, from first law of thermodynamics, delta Q is equal to delta U plus delta W. But for adiabatic process, delta Q is equal to 0. Therefore, delta U plus delta W is equal to 0. Therefore, delta U is equal to minus delta W, or delta W is equal to minus delta U. What is the meaning of this equation? It means the work done by a gas. When the work done by a gas decreases the internal energy of a system. Delta W is positive, that means the work done by the gas on the environment. So what's happened? The internal energy of the system is decreased because there is negative. If the delta W is negative, that means the work done on the system. Work done on the system of the gas. So internal energy of the system is increased. Internal energy of the system is positive, that means the increase. Here negative, so that is the decrease. Again, for adiabatic process, exchange of the heat is 0. Delta Q is equal to 0. Therefore, from first law of thermodynamics, delta U is equal to minus delta W, or delta W is equal to minus delta U. Now in equation 1, we are using this relation, delta W is equal to minus delta U. Delta U is positive. It means work done by the gas on the environment decreases the internal energy of the system because the delta U is minus. Now, from this relation, delta U is equal to minus delta W. Work done is negative. That is, work done on the system by the environment increases the internal energy of a system. Clear this? Okay. For an ideal gas in adiabatic process, PV is to gamma is equal to constant. What is the gamma? Already we discussed gamma is equal to Cp upon Cv, the ratio of two specific heat capacity at pressure and the specific heat capacity at constant volume. Again, for an ideal gas, in adiabatic process, PV is to gamma is equal to constant. For isothermal process, we take the PV is equal to constant only. Now keep in mind this relation. For adiabatic process, PV is to gamma is equal to constant. Here the gamma is equal to Cp upon Cv. Cp is the specific heat capacity at constant pressure and Cv is the specific heat capacity at constant volume. Yeah. So in short, for an ideal gas in adiabatic process, PV is to gamma is equal to constant. Now we are interested to obtain the work done for adiabatic process. Right. For that purpose, suppose an ideal gas goes adiabatically from initial state P1, V1, temperature T1 to the final state pressure P2, volume V2 and temperature T2. The work done for small changes in volume delta W is equal to P delta V. Now, the work done for small changes in volume delta W is equal to P delta V. Therefore, total work done for entire process is obtained by taking the integration. Therefore, W is equal to integration of delta W is equal to integration of V1 to V2, value of delta W, P dV. Now, for adiabatic process, PV is to gamma is equal to constant. Therefore, what is the value of P? P is equal to constant upon V is to gamma. Substituted here, therefore, work done W is equal to constant. Integration V1 to V2 instead of P, we add down the work upon V is to gamma into D. Actually, P is equal to constant upon V is to gamma. Constant is taken out of integration. Therefore, constant into integration V1 to V2, 1 upon V is to gamma into D. So 1 upon X, we can add the X is to minus 1. So using this concept, the constant integration V1 to V2, V is to minus gamma into dV. V is to minus gamma into d. Okay. Before taking the integration of this, again we repeat, what is the adiabatic process? The process during which there is no exchange of the heat between the system and its environment is known as adiabatic process. Exchange of the heat is zero. Now, from first law of thermodynamics, delta Q is equal to delta U plus delta W. But for adiabatic process, delta Q is equal to 0. It means delta U plus delta W is equal to 0. That means the delta U is equal to minus delta W or delta W is equal to minus delta U. Okay. It means, what is the meaning of this? Delta W is positive, therefore work done by the system on the environment so decreases the internal energy. Now, if the work done is negative, that means the work done on the system by the environment increases its internal energy. Now, for an ideal gas in an adiabatic process, PV is to gamma is equal to constant and gamma is equal to Cp upon Cv. Okay. Suppose an ideal gas goes adiabatically from initial state, pressure P1, volume V1, temperature T1 to the final state, pressure P2, volume V2 and temperature T2. Now the work done for small changes in volume, delta W is equal to P into delta V. Therefore, total work done for entire adiabatic process is obtained by taking the integration. Therefore, W is equal to integration of delta W. Substitute the value of delta W. Integration P dV. Value of the volume changes from V1 to V2, initial state to the final state. Therefore, integration V1 to V2 P dV. But for adiabatic process, PV is to gamma is equal to constant. Therefore, P is equal to constant upon P is to gamma. Here we substitute the value of P. Therefore, W is equal to integration V1 to V2. Constant upon V is to gamma into dV. Constant is taken out of the integration. Therefore, W is equal to constant integration V1 to V2 1 upon V is to gamma into dV. Again, constant is taken out of this integration. Constant into integration V1 to V2 1 upon V is to gamma dV. Now, we know that the 1 upon X is equal to X is to minus 2. 1 upon X square is equal to X is to minus 2. Using this concept, therefore, constant into integration V1 to V2. 1 upon V is to gamma, that is the V is to minus gamma into dV. V is to minus gamma into dV. Clear this? Okay. Now we have to take the integration of this part. What is the integration of V is to minus gamma into dV? So already we know that 1 upon X is to n into dx is equal to X is to minus n into dx. Now using the standard equation of integration, so X is to minus n plus 1 upon minus n plus 1. So integration of the power term, this type of the term X is to n into dx, so power is increased by 1 and new power also in denominator. Therefore X is to minus n plus 1 and new power is minus n plus 1 is in denominator. So X is to minus n plus 1 upon minus n plus 1. Clear this? Okay. Using this, therefore constant as it is, integration of V is to minus gamma is V is to minus gamma plus 1 upon minus gamma plus 1, value varies from V1 to V2. V1 to V2. Okay. Now, this term is taken out. Minus gamma plus 1, that means the 1 minus gamma. Therefore, constant upon 1 minus gamma. Here, what's happened? V is to minus gamma plus 1, value varies from V1 to V2. Substitute the value, therefore constant upon 1 minus gamma, V as V2, therefore V2 is to minus gamma plus 1, minus initial volume V1 minus V1 is to minus gamma plus 1. Again, the integration of V is to minus gamma 1, V is to minus gamma is V is to minus gamma plus 1 upon minus gamma plus 1. Value varies from V1 to V2. This term is taken out of this bracket, that is independent of V1 and V2. So gamma minus gamma plus 1, that is the 1 minus gamma. Therefore, constant upon 1 minus gamma. Remaining term is only V is to minus gamma plus 1. Value of V varies from V1 to V2. Now, constant upon 1 minus gamma. Substitute the V as V2 and V1 is subtract from the V2. Therefore, V2 is to minus gamma plus 1 minus V1 is to minus gamma plus 1. Minus gamma plus 1. Okay. Therefore, constant upon 1 minus gamma. Here we take the constant inside. Therefore, 1 upon 1 minus gamma. Constant upon V2 is to gamma minus 1. We take this term in denominator. Therefore, power again becomes the negative. So now in numerator, gamma is negative, 1 is positive. So in denominator, gamma is positive, 1 is negative. Therefore, constant upon V2 is to gamma minus 1 minus constant upon V1 is to gamma minus 1. So keep in mind that here the simplification is quite difficult. As we go step by step and we understand the each and every step, so that is very easy. Right? So here again, constant upon 1 minus gamma, V2 is to minus gamma plus 1 minus V1 is to minus gamma plus 1. We take the constant inside the bracket. So remaining is 1 upon 1 minus gamma into bracket constant upon. This term is taken in denominator, therefore power becomes the negative. Here the power is minus gamma plus 1, it becomes the gamma minus 1. Therefore constant upon V2 is to gamma minus 1 minus constant upon V1 is to gamma minus 1. Okay. Now we know that the constant PV is to gamma is equal to constant for adiabatic process. So we can add the P1, V1 is to gamma is also constant, P2, V2 is to gamma is also constant. Therefore, constant is equal to P2, V2 is to gamma is equal to P1, V1 is to gamma. So instead of the constant, we substitute the relative value. Here in denominator V2, so in numerator we substitute the P2, V2. Here in denominator V1, so in numerator we substitute the P1, V1. Therefore, W is equal to 1 upon 1 minus gamma. Bracket P2, V2 is to gamma upon V2 is to gamma minus 1. Minus P1, V1 is to gamma upon V1 is to gamma minus 1. Now, again, take this denominator term in the numerator. So, again, the power becomes the negative. Therefore, 1 upon 1 minus gamma into bracket P2, V2 is to gamma into V2 is to minus gamma plus 1 minus P1, V1 is to gamma into V1 is to minus gamma plus 1. Here the base are same, therefore addition of the power. So V2 gamma minus gamma plus 1. Here the V1 gamma minus gamma plus 1. Gamma gamma cancel, only here V2 remaining, here the V1. Therefore, W is equal to 1 upon 1 minus gamma. Here P2, V2 minus P1, V1. Right? Okay. But from equation of the state of an ideal gas, PV is equal to mu RT. Therefore, P1, V1 is equal to mu RT1 and P2, V2 is equal to mu RT2. Mu RT. We substitute it here. Instead of the P2, V2, we take the mu RT2. And instead of the P1, V1, we take the mu RT1. Therefore, W is equal to 1 upon 1 minus gamma into bracket mu RT2 minus mu RT1. Mu I is common upon 1 minus gamma, T2 minus T1. Yes, here it is gamma minus 1. So here negative sign is common, T1 minus T2. Therefore, W is equal to mu R, T1 minus T2 upon gamma minus 1. That is the equation of the work done for isothermal process. That is the equation of work done for, adiabatic process, not isothermal. For adiabatic process. Therefore, if the work done by a gas, work done by the gas on the environment, W is positive, therefore T1 minus T2 is greater than 0. It means that T1 is greater than T2. Temperature, the initial state is more than the final state. Means the temperature decreases. Okay, if the work done on the system by the environment, so here what's happened? W is negative. Therefore, T1 minus T2 is less than 0. Therefore, T1 is less than T2. It means the temperature increases. Temperature is increased. Again, if the work done is positive, that means the work done by a gas, W is greater than 0. Therefore, T1 minus T2 is greater than 0. It means that T1 is greater than T2. That means the temperature decreases if the work done by a gas on an environment. That means the volume is expanded. Temperature decreases. Work done is positive. Now, if the work done on the system, what's happened? Work done W is less than 0. So in that case, T1 minus T2 is less than 0. That means the T1 is less than T2. It means the temperature is increased. In short, if the work done by the environment on the system, so system is compressed, work done is negative, and temperature is increases. Temperature is increases. Clear this? So this is the important for MCQ type question. Again, what is the adiabatic process? The process during which there is no exchange of the heat between the system and its environment is known as the adiabatic process. Now, from first law of thermodynamics, delta Q is equal to delta U plus delta W. For adiabatic process, delta Q is equal to 0. Therefore, delta U plus delta W is equal to 0. That means delta U is equal to minus delta W, or delta W is equal to minus delta U. It means that if the work done by the gas, W is positive, so decreases the internal energy of the system because the delta U is negative. Okay. According to this relation, delta U is equal to minus delta W. If the work done on the system by the environment, therefore the work done is negative, at that time the change in internal energy is positive, it means the internal energy of the system increases. Clear? Okay. Now for an ideal gas in adiabatic process, the relation between the pressure and volume is PV is to gamma is equal to constant. For isothermal process, we consider PV is equal to constant. For adiabatic process, the relation between the pressure and volume is PV is to gamma is equal to constant, and gamma is equal to Cp upon C. Cp upon C. Now we assume that suppose an ideal gas goes adiabatically from its initial state P1, V1, T1 to the final state P2, V2, T2. Here the gas or the system changes its state from initial to the final adiabatically. In initial state, pressure is P1, volume is V1, temperature is T1, while in final state, pressure is P2, volume is V2, and temperature is T2. Therefore, the work done for small changes in volume, delta W is equal to P delta V. Work done, delta W is equal to P delta V. Therefore, total work done for entire process is obtained by taking the integration. Therefore, integration delta W is equal to, substitute the value of delta W, integration P dV, and volume changes from V1 to V2. But for adiabatic process, PV is to gamma is equal to constant. Therefore, P is equal to constant upon V is to gamma. Substituted here, constant is taken out. Therefore, W is equal to constant into integration V1 to V2, 1 upon V is to gamma into dV. We know that 1 upon x square is equal to x is to minus 2. Therefore, 1 upon V is to gamma is the V is to minus gamma. Therefore, this equation W is equal to constant into integration V1 to V2. Instead of the 1 upon V is to gamma, we can add the V is to minus gamma into D. Now, integration of this term, according to this equation, standard equation of integration, 1 upon x raised to n into dx is equal to integration of x raised to minus n into dx. Here the power is n, therefore its integration of power term is increased by 1 and new power is in denominator. Therefore x is to minus n plus 1 upon minus n plus 1. Therefore integration of v is to minus gamma is v is to minus gamma plus 1 upon minus gamma plus 1. Substitute here. Therefore, constant as it is, integration of this part is V is to minus gamma plus 1 upon minus gamma plus 1 when you raise from V1 to V2. This minus gamma plus 1 is taken out. We can add as 1 minus gamma. Therefore, constant upon 1 minus gamma. Remaining term in bracket V is to minus gamma plus 1. Volume changes from V1 to V2. V1 to V2. Therefore, constant upon 1 minus gamma. First we substitute the final value of volume. V2 is to minus gamma plus 1 minus. Instead of V initial volume, V1 is to minus gamma plus 1. Right? Okay. We add again this form. Again in reciprocal form. Therefore, constant taken inside. Therefore, 1 upon 1 minus gamma. Constant upon V is 2. Power becomes again negative. Therefore, gamma minus 1. Constant upon V2 is to gamma minus 1 minus constant upon V1 is to gamma minus 1. Only the mathematical simplification. But for adiabatic process, PV is to gamma is equal to constant. Or in other words, constant is equal to P1, V1 is to gamma is equal to P2, V2 is to gamma. Now in first term, in denominator, here the V2 is given, therefore instead of the constant, we can add the P2, V2. While in second term, in denominator V1, so in numerator, instead of the constant, we can add the P1, V1. Therefore, total work done W is equal to 1 minus gamma into bracket. Instead of this constant, P2, V2 upon V2 is to gamma minus 1. Minus, instead of this constant, P1, V1 is to gamma upon V2 is to gamma minus 1. Again, this equation is that form. W is equal to 1 upon 1 minus gamma into bracket P2, V2 is to gamma upon V2 is to gamma minus 1. Minus P1, V1 is to gamma upon V1 is to gamma minus 1. Again, we take the V2 is to gamma minus 1 in numerator and V1 is to gamma minus 1 in numerator. Again, the power becomes the negative. Therefore, 1 upon 1 minus gamma, P2, V2 is to gamma into V2 minus gamma plus 1. Now second term minus P1, V1 is to gamma into V1 is to minus gamma plus 1. Here the base are same, therefore the addition of the power gamma minus gamma plus 1, gamma gamma cancel, only V2 is to 1. Here also V1 is to gamma, V1 is to minus gamma plus 1, base are same, therefore the addition of the power gamma minus gamma plus 1, gamma gamma cancel, only V1. Therefore, W is equal to 1 upon 1 minus gamma, remaining is P2, V2 minus P1, V1. Now, the equation of state of an ideal gas. P1, V1 is equal to mu R T1 and P2, V2 is equal to mu R T2. Okay, substitute here the value. Therefore, W is equal to 1 minus gamma mu R T2 minus mu R T1. Mu R common, therefore mu R upon 1 minus gamma T2 minus T1. As we add the T1 minus T2, so negative sign common, this negative sign multiply with the denominator term, therefore it becomes the gamma minus 1. Therefore, work done W is equal to mu R T1 minus T2 upon gamma minus 1 is the equation of the work done for adiabatic process. W is equal to mu R T1 minus T2 upon gamma minus 1. Now, from this equation, if the work done by a gas, that means the work done is positive. W is greater than 0. So, right hand side of this equation, T1 minus T2 is greater than 0. That means the T1 is greater than the T2. Therefore, the temperature is decreased. That means if the work done by the system on environment, system is expand, work done is positive, and temperature of the system is decreased. Now, if the work done on the system by the environment, see, environment doing the work on a system, so system is compressed, work done is negative, therefore T1 minus T2 is less than 0, therefore T1 is less than T2. That means the final temperature is more than the initial, it means the temperature increases. So that is the equation of the work done during the adiabatic process. Clear it? Oh.